All right, so in this video, we're going to look at specific cases where there could be functions that are continuous at points, but they still fail to be differentiable at these points. So this first theorem, or theorem 2.1, says that if you can show that a function is differentiable at a point x equals c, then you could say it's continuous. However, you can say the opposite. You can't say if a function is continuous at x equals c, that it's differentiable, and we're going to see why in these examples. So let's first look at the function f of x is equal to the absolute value of x minus 2. As we know, or as we should know, this is an absolute function, or absolute value function, that has an x-intercept at 2, 0. And, on the right side, it's going to be going, has a slope of 1. So it's going to be looking like v going like that. And on the other side, it's going to do this sort of action. Okay, so geometrically, if you just look at this and recall what I explained in the previous video, at the point 2, 0, the function is going to fail to be differentiable because it comes off as like a sharp point. The slope coming from this side, from the right side of the graph, is negative, whereas the slope coming from the left side of the graph is, the slope coming from the right side is positive and the slope coming from the left side is negative. So they're actually not equal at this point. And so it's not going to, have a derivative that we can say is equal if you were to approach it from the left and from the right at x equals 2. But let's go through how we show this formally and algebraically through some calculations. So we would have to go back and discuss the one-sided limits, if you recall. So we talked about the one-sided limits at x equals 2. So the one-sided limits at x equals 2 are, let's look at the left and let's look at the right. So the limit as x approaches 2 from the negative side, and then the limit as x approaches 2 from the positive side. So we're going to look at how they both compare. And just to kind of re-clarify, the limits from both sides are the same at 2, but I'm referring to the derivative, or the slopes. So if we're going to calculate the slope coming from this side, the left side, we would do something like find the difference between the function and f of 2. So let's go right to f of x minus f of 2 over x minus 2. And let's just write what this is, formally, as we've been doing with calculating derivatives. So the limit as x approaches 2 from the negative side, probably should have a little smaller. So f of x is defined as the absolute value of x minus 2. And f of 2 would just be 0, because 2 minus 2 is 0. So we just have that minus 0 all over 2 minus 2. Let's leave that as just x minus 2. And then let's just look at what this is going to equal by analyzing the graph. If we're coming from this side, we can tell that we're just going down 1 to the right when our slope is just -1. So this is going to be equal to -1. the derivative from the left side is -1. But the derivative from the right side, from this side, is +1. That's right, +1. And over here, we'll write, emphasize that we're analyzing the slope. So we would write essentially the same, expression, f of x minus f of 2 over x minus 2 equal to the limit as x approaches 2 from the positive side. Absolute value of x minus 2 minus 0 over x minus 2. And now just be positive. We'll just write 1. So since these two slopes or these two values are not equal, then this function fails to be differentiable at x equals 2. Or these two limits. Are not equal. Is not differentiable at x equals 2. All right, now let's look at one more case. And we're going to focus on the function f of x equal to x to the 1/3, the cubic function. So if you remember what this looks like from your pre-calc class, it's going to do some weird sort of curvature thing. It's going to go through 0, 0, and we can take a third root of negative numbers, so we can have negative values at -1, -1, and 1 at 1, 1. And then it would have third root of 8, so it's 1, 2, 3, 4, 5, 6, 7, 8. Just to get an idea, a better picture of it. 8, 2, and then we would have a third root of -8. -8, -2. So the graph does something like this. Roughly speaking, at least. Now we know the graph is continuous, all along, all along this domain, and it's defined for, all real numbers x. But what happens at the origin? Like, what is it exactly that the graph is doing? Like, what would the slope of the derivative be? So let's study that. Let's study that. Let's study that point and calculate the limit over there. So let's look at 0, 0. So the limit at x equals 0 is, so we're going to take just the limit in general, because we can't, say for sure that, it's different from one side than it is from the other side. It's not obvious. So we're going to take the limit as x approaches 0 of f of x minus f of 0, just our regular, formal equation over x minus 0. That will be equal to the limit as x approaches 0. F of x is defined to be the third root of x, so x to the 1/3. F of 0, the third root of 0 is just 0, so that's just minus 0. Over x minus 0, which is just x. And so then we have x to the 1/3 over x to the 1, which will be just 1 over x to 2/3. So this will be equal to the limit as x approaches 0 of 1 over x to the 2/3. Now, so what do we do here? Well, as you can see, if you plug 0 into x here, we would have 1 over 0. We would have, undefined value. This would, be essentially be 1 over 0. And we are going to learn that this is going to be recognized as a form of infinity. We're going to go more into that in mathematical, terms later on in this course. But for now, just understand that what's going on is that 1 is an infinitely large number compared to 0. It's so much bigger than 0 that we just say that this expression is essentially, the same as what infinity is. Infinity is not a number again, so we can also say that, or it does not exist. That's another acceptable answer. But essentially, there's a vertical tangent line at the origin. Because as we can recall from the previous math life, when we were taking the slope of a ratio where you were dividing by 0, because you had a vertical line, y equals or x equals something. So we just basically say that since there's a vertical tangent at x equals 0, the function is not differentiable here. It is not differentiable here. All right, so that's all there is to it.